Hey everybody, it's Mrs. Cassell, and here's Friday quiz number 21. I'm not going to read the whole thing because it's a lot of reading. So take a second here and pause the video and read the problem for yourself. Okay, so either pause it or you're ready for the solution. So first things first, the correct answer down here is Badu. Okay, so let's go ahead and think through what he answers. They both have the same energies. All right, so when I look at what we're starting with down here, we've got two objects. They're being compressed the same amount on the spring. They have the same spring constant K. So this is my X. This is the K right here. If I think about the elastic potential energy that these are being given at the bottom, the equation for elastic potential energy has nothing to do with the mass of the object. It's about the spring. What are you doing to the spring? What happens after that may depend on the mass, okay? So in terms of what energy they're starting with, because they're being compressed the same, because they have the same spring constant, they have the same initial energy because it's all elastic potential energy. So what else does Badu say here? He says they have the same energy at the top. Okay, well that's true. The law of conservation of energy says that whatever total energy you have when you start with is the same when you end. And why can we trust that in this situation? Because of one of the clues in the story problem, which is that this is a frictionless ramp. So we have no non-conservative forces that are present, right? So the lag on my computer is nuts, you guys. All right. So the last part is that he says, so the lighter mass has to go higher. That can be a little hard to reason through. I'll admit that for me, it helps me to kind of think through the math of that. So in my box down here, I'm going to work it out, which is what I asked you to do on the back of your paper. If both of these have the same energy to start with, and I could figure out what that number is, right? Because the elastic potential energy is going to be equal to that spring constant times 1/2 times the amount of compression squared. And then I'm going to go ahead and think about all that energy when it gets to the top. It's coming to a stop. That means velocity equals 0. So there's no kinetic energy at the top. It's not touching the spring, which means at the highest point at the top, the only type of energy that's present is gravitational potential energy. So whatever this elastic potential energy is that I might calculate down here, it's going to be equal to the gravitational potential, energy at the top. So to win this argument, I don't even need to do the math, right? I could make up a number. I've used the law of conservation of energy to justify that I can say they have the same initial energies. But let's go ahead and figure it out. My initial elastic potential energy is going to be 1/2 times 250 newtons per meter times 0.5 meters, that's squared. So I put that in my calculator. Boop, 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 boop. There's my calculator. Hi, calculator. 0.5 times 250 times 0.5 times 0.5. All right, I got 31.25 joules. That's my initial energy at the top. So gravitational potential energy is equal to mass times the acceleration of gravity times the height. And I've just said that this energy is going to be equal to my total gravitational potential energy. So I'm going to go ahead and do the algebra to solve this for height, right? I'm curious how high they're going to go. So if I want to know how high they're going to go, it's going to be whatever energy I have divided by the mass of the object times the acceleration of gravity. You could also win this argument by just rearranging this equation here, and you can show that because mass is in the denominator, as the mass increases, the height must decrease. It's inversely proportional. So now we're going to go ahead and solve for the number if you want to do that. So let's figure out how high the height that object A is going to go. It's going to be 31.25 joules divided by its mass was 1 kilogram times 9.8 meters per second squared. All right, do that in my calculator. 31.25 divided by 1. I did just type that in my calculator. Divided by 9.8. Can estimate 10 for all of these. 3.19 meters. That's the height that object A is going to reach. Let's do the same thing for object B. 31.25 joules because of the same initial energy. So at the top they must have the same gravitational potential energy, but I've got 5 kilograms of mass that's making use of that energy times 9.8 meters per second squared. So now, when I type that in my calculator, 31.25 divided by 5 divided by 9.8. Wow, that's a much smaller number. Just checking. That makes sense. If I take that other answer and divide it by 5, I should get that, right? 0.64 meters. So the lighter object travels to a greater height. The heavier object travels to a lower height.